All right. So this is going to be an update on the OCP Heat Reuse, the Reference Designs workstream. I'm David Sickinger. I'm a researcher at the National Renewable Energy Laboratory, NREL, as well, and my focus is on energy-efficient data centers and liquid cooling. So Mark Smith is actually going to start off with the first portion, and then I'll follow up. So turn it over to Mark.
Hello everybody, my name is Mark Smith. I am a key account manager at Alfa Laval, and my focus is on how our heat exchanger technology can help to facilitate the cooling and removal of the heat from data centers, and with that, heat reuse as well. I would like to reiterate what Otto said previously. Start with the mindset of just doing something. If you have a 20 megawatt data center, don't think, hey, I need to reuse 20 megawatts worth of heat. You know, maybe you use some of that heat to heat your office space inside the data center. Something is better than nothing. So this is very outside of my comfort zone, and I figured what better way to do this than start with something that I've never told anybody before. One of my guilty pleasures since I was young is long hot showers, and I understand how wasteful and not sustainable that is, but when I was in high school, it occurred to me of how much heat and energy was going down the drain, and I thought of, how could it be possible to kind of use that heat to preheat the water going back into the hot water tank? And I share that story just because that's the kind of mindset that I think is important to have of, what can be done with what options are available to us. I was also smart enough to know not to mess with the plumbing system in my dad's house, so never went anywhere with that. But getting into the presentation, the purpose of the Heat Reuse Reference Design workstream is to define a set of common features of basic technical room in a data center for heat reuse purposes, and create guidance that engineers, architects, and decision makers might utilize when designing and developing a data center that facilitates the recovery of excess heat. We cover a variety of topics, including basic componentry required to facilitate this heat reuse, the space requirements, demarcation point between the data center and the heat user, and the impact of the different scenarios that have on defining this point. We also look at business considerations, the different stakeholders involved, and the impacts of heat reuse on the data center metrics. So let's take a look at a simple scenario of a liquid-cooled data center where the components required to implement heat reuse, where this additional equipment can be located, and the considerations that should be given to the space needed. The base case in our paper is a 1 megawatt data center design, but we also look at the impacts of a larger IT load up to 5 megawatts for comparisons. The rendering on the left side of the screen depicts a separate heat reuse room, but this equipment can also be located inside the data center's mechanical room. In our white paper, we take a detailed look at the factors that influence how much space is required, but a general rule of thumb for a simple basic heat reuse system is between 3 and 6 square meters per megawatt of heat being reused. The majority of the space is for the liquid-to-liquid heat exchanger, which is critical for making heat reuse possible. As the chart on the right-hand side of the screen shows, the other components required include sensors, gauges, meters, flow control actuator, and valves. All typical mechanical components, nothing special just for heat reuse. All of this can be located in the piping and the ceiling, so not too much extra space is required for that. The bottom section of the chart shows, I forgot to turn. Bottom section of the chart shows some components that may be required depending on the data center design, as far as extra or dedicated pumps to the heat reuse loop if boosting of the pressure is required. Now we're going to take a look at the line diagram on the screen here. This depicts the relative location of the components that I just discussed and how they kind of all go into the system together. On the left side of the diagram is your data center room, or data center side of the system, and that dotted line is a bypass option. So if there is no demand from the heat user for heat, then the heat reuse system would just be bypassed and the traditional cooling methods for the data center will be utilized. On the right side of the screen, you'll notice that on the bottom part of the screen here is we call out the demarcation point. So this is where kind of ownership transfers from the data center to the heat user. In this scenario, it's critical to have it there because some of the sensors on that side of the heat exchanger are utilized to control the system for the data center cooling. Let's now take a look at our stakeholder map contributed by nThe Innovation Hub, who, as announced this week, is now a partner with OCP. So this defines the interface nomenclature spanning from the data center to heat transmission to heat user and various stakeholders that will likely be involved. The current focus of our paper is on the data center heat distribution, over here, the heat recovery room or station, which we will discuss in the next slide, and the heat transmission and heat delivery station. So this is a concept of a heat recovery station, so more of a modular form factor, credit again to NZIH. This can either be an open skid or an enclosed containerized design as shown here. So the same components that I've discussed on the previous slides are also involved and utilized in this design, but this concept of modularity kind of opens up some benefits that everybody associates with modularity design, space savings, ease of scalability, and speed of deployment. As you can see here, this design utilizes 2 heat exchangers for redundancy purposes, and that's something that we discussed in the paper of what levels of redundancy are required for heat reuse systems. It's important to note that inherently the heat reuse system is a redundant, it's adding a layer of redundancy to the data center. It's one extra way that heat can be rejected. So looking at 2 different types of data centers, we have air-cooled on the bottom left here, producing around 20 C liquid, and then direct liquid cooled on the top left, producing around 35 C liquid. We examined the different scenario paths possible with the different grades of heat. It will most likely be the case that for air-cooled data centers, a heat pump will need to be utilized to increase that fluid temperature to match the heat user's requirements. A heat pump or a high-temp heat pump may also be employed in direct liquid cooled data centers to further increase the temperature as well. On the right side of the screen, we kind of break it down into 3 different tiers of heat users and the temperatures that they require. So on the bottom here, our low tier, greenhouses and public swimming pools are 2 examples for the low heat. Applications with that may only require that design that I showed before with just a heat exchanger, no heat pump elevation of temperature is required. Once we start looking at the medium temperature heat users, in the middle here, such as radiator heating or 4th generation district heating, and the high temperature heat users, breweries, pasteurization processes, other industrial processes, it's pretty likely that the heat reuse design will need to utilize some type of heat pump. And now I'm going to turn it over to David to discuss his experience with heat reuse at NREL.
Okay, thanks, Mark. So the graphic here in the upper right is just sort of showing a generic hybrid data center scenario where you could have both air-cooled IT equipment that's relying upon computer room air handlers along with chillers, but also mixed then in with a direct liquid cooled system. So opportunities for heat reuse and dry cooler go up. That's just sort of a generic concept design. The graphic here on the left, though, is just sort of based upon some of NREL's lessons learned from our high-performance computing data center. It's been in operation for over a decade. It was designed with direct liquid cooling in mind, along with heat reuse. But we only had one facility loop, and so that kind of creates some challenges in diluting the overall temperature to the heat user. In our case, we're the end user of the heat within our building and on our campus. So, the single facility loop that is trying to support both air-cooled and liquid-cooled is challenging because it's the air-cooled equipment that is usually the limiting factor. So we typically supply 20 degrees C, max 24 C, and that in turn keeps our blended return temperature in the range of 32 to 35 C. And so for heat reuse, the way we're doing it is we just have a heat exchanger, sort of Mark talked through sort of the basic scenario. And so over the course of a year, I think the best we've done is sort of recovered 11%, but still it's great in the sense that we just added a heat exchanger in order to enable that. So it's just do something. But what we're trying to show here with this graphic is if we could do it again, we might think about having two-loop facility system. So a medium temperature water loop here, sort of showed in this bottom left, that would sort of serve your air-cooled traditional IT equipment. Could also be for the rear door heat exchangers. And then in the upper left here would have a high temperature loop for the direct liquid cooling, and this would be for more of the immersion based cold plate type solutions. Then what we're trying to show here on the right here is sort of the hierarchy of heat rejection options that you have to consider as you're designing and thinking about how you're going to operate your data center, sort of with a preference in the starting in the top upper right. So if you can get by with just a heat exchanger for your heat reuse, that's great, especially if you can start thinking about like supplying W45 or higher to your liquid cooled systems. Next option then is sort of adding in a heat pump as part of that to boost the temperature to what you might need. And then, when heat reuse potential is exhausted, looking at dry coolers then, especially for like water stressed areas. And then, ideally if you can get by with just cooling towers, they're energy efficient but consume lots of water, and eliminate chillers or maybe limit their use to just sort of trimming during certain times of the year is sort of an approach that we sort of suggest and recommend. So the company Cloud and Heat contributed towards a section of on heat transformation options. So there are other things that can be done. There is seasonality and intraday variations, both on the data center side, depending on the production type of workload that is run. We can also see that on the side of the heat user in terms of what they might need. It could also vary by day or by season. So thinking about here, say sort of flagged, including like a thermal storage tank gives you some different options as the complexity goes up a bit, but these are the things to sort of think through as you're designing a new data center or major retrofit. And then also, we sort of have another option then is, our recommendation, general recommendation is think first about using heat for heat, but there is then using heat for cooling. So there are ways to do that. By generating cooling driven by thermal energy, either adsorption or absorption refrigeration. But in order to kind of really drive those processes in that chiller system, you need 45 C or higher, and really it's 55 C for improved coefficient of performance. And then if you're kind of looking at absorption chillers, really the minimum starting point is 65 C. So again, some additional reasons why we sort of encourage, as you're thinking about liquid cooling, higher supply temperatures give you the higher return temperatures. It raises the options of what you can do with that. So the OCP, so looking at metrics and potential benefits, this has been discussed a little bit, but the OCP Data Center Facility Sustainability Subproject under the Energy, Heat, Water workstream. They've been working on a white paper and looking at the influence of heat reuse on energy and water consumption and carbon emissions. It's been discussed a little bit before, but so maybe I'll just kind of highlight a little bit here. This particular scenario is just showing if you just are using heat with just a heat exchanger, but it still provides benefits of reduced mechanical cooling. That has impact on your power usage effectiveness, directly lowering the energy use, indirectly lowers your water usage, and then also indirectly lowers your carbon footprint. If you're reducing your evaporative cooling in your data center, again, lower energy, definitely lowers the water usage, less evaporation, and then indirectly lowers the carbon footprint. And then on the heat hose side of things, we've already sort of talked about that, is it's lowering the energy used for your heating system. So, the potential benefits are both for the data center side, looking at if you can monetize the sale of the heat, cutting power cost and carbon footprint, and then on the end user side, replacing natural gas with data center heat, cutting the cost and carbon. So we are having monthly meetings on the first Thursday of the month, so the next one will be on November 7th. What we are targeting to do is publish this initial white paper by the year end. So if interested, invite you to review and provide feedback. We're sort of looking for that by November 22nd timeframe. And opportunity for recognition still if you are able to contribute material. So looking for additional examples and scenarios to think through. And then, because we could definitely use some more information on different scenario combinations from air cooling to moderate and high temperature liquid cooling. And so with that, let's see, oh, looks like we're at time here. So thank you, and feel free to reach out to Mark and myself. We'll be happy to follow up if there's questions, and we'll kind of hang around after this as well for a bit.